Good afternoon. I'm Niklas Schmalholz from POLIS Network. Welcome to this webinar, which will discuss the NextETRUCK aspects and the status of the zero-emission heavy-duty vehicles industry, trucks specifically. And I will give you a brief introduction, and then my NextETRUCK colleague, Stephen, will take over. So basically, the webinar is recorded, and afterwards the recording will be published on our website and on our YouTube channel on nextetruck.eu. That's our website. And if you have any questions, please share them in the chat. No need to use the Q&A. It's easier, so I can interact with you. And Stephen will probably take these questions at the end. And I will select the questions, and in case there's something urgent, I will interfere if necessary. So since I'm the communication manager of the NextETRUCK, I always find it very important to share with you the communication information. So you can find us on LinkedIn, of course, linkedin.com/company/NextETRUCK, and that's our main hub on nextetruck.eu. Those are the QR codes. I will give you a couple of seconds to scan them. Please follow us on LinkedIn. There you will get all the updates also for further upcoming webinars or events. Our next upcoming event is probably our kickoff of the pilots that will start in May in Barcelona, but we have not yet confirmed a date of this event. But if you are following us on social media, or if you follow our newsletter or subscribe to that, then you will get all that information. So I will briefly talk about what can you expect today. So the entire idea started last September when Stephen Wilkins gave a great internal presentation during our consortium meeting. And then I asked him, hey, wouldn't this be something super relevant to the wider audience? Because he went into several important topics related to the zero-emission freight sector. So what are the latest developments, but also what are the newest models of these electric trucks, and also what are the colleagues that are doing research on hydrogen trucks and those pilots are working on, and what are the use cases. So when could we use which vehicle, which zero-emission freight vehicle, and when it is better to use electric or hydrogen. And today we are not going to talk a lot about the NextETRUCK project itself, but we are more looking at the wider picture, which will be done by Stephen. So he has a PhD in mechanical engineering, so he's very much aware of what is going on, and so he can explain everything in great detail. And his current position is the senior research scientist at TNO, and TNO is our coordinator of the NextETRUCK project, and he's also an assistant professor at the TU Eindhoven. So I will give the floor to you now, Stephen.
Okay, thank you. So just to check, you can see my screen okay?
No, you still have to share it. Please do that again.
There we go. Yes. Okay, perfect. So yeah, to start off, yeah, firstly, it's a pleasure to have a chance to present on this topic today. Thank you for POLIS for organizing it. So as described, the aim of this webinar is to give a broad view of where we are, where we're going, and some of the challenges and opportunities that we see in this sector. So I'm going to start with this picture. This is an updated version of an image that was circulating when we were in COVID at the beginning of the decade. Of course, we have several significant challenges presenting themselves at a global level. Of course, the conflict in Ukraine, uncertainty on supply chain, certainly relations with China, with the US, etc. But the biggest challenge that we need to address during this decade is to prepare ourselves for mitigating climate change. And it's as quoted here, it's going to be a very decisive decade to realize the technologies, solutions, and the direction that we're going in from a European standpoint. So today I'm going to talk about three main challenges which are related to climate change. And the first one I'm going to talk about is really the big picture. So how are we going to meet net zero for trucks? And I put a small comment on the bottom right, and this is true of any type of presentation or any discussion here. We need to be careful about dogmatism when we talk about solutions here. Yes, everyone has different biases towards technology, but to get there, we really need to have an open discussion and not fixate on any single solution. So the challenge today is to meet, in the end, net zero by 2050. That means that there's no net CO2 being produced from the truck sector, not only for new vehicles, but also the deployed fleet. That means that to reach that goal, we have to start selling zero-emission vehicles much, much earlier. And the dark green line here is now the new adopted policy from the European Commission, which sets targets from 2020 as a baseline, 2029 as a technical baseline, to realize in 2030, 2035, 2040, ultimately to realize full zero-emission vehicles as we approach 2050. So here you can see these were a lot of the discussions on what policy direction we should take. There were, let's say, more conservative manufacturer-led targets versus, let's say, more aggressive. And in the end, Europe adopted a middle way policy. And the targets here are specific to each of the years. So those targets are set for all heavy-duty vehicles. In detail, though, they're broken down per sector within the heavy-duty transport market. So it's summarized here per year, per vehicle type, per mass of the contributing sectors towards CO2 reduction. So these are now the targets that we need to meet in terms of sales of zero-emission vehicles as we approach 2030, 2035, 2040, etc. It's worth also saying that there is other non-EU level policy coming into place. So on a local level, certainly from city level, 2025 sees the introduction of zero-emission zones. And these are not only concerned with CO2, they are mainly focused on tailpipe emissions, often prohibiting engine operation within those zones. But these two policy directions, both at local level and from member states and at European level, set some of the challenges that we need to meet with the various technologies. So if we look at the types of technologies and this transition pathway, this is a figure pulled from ASEA, so the representation of the European manufacturers. The transition away from fossil fuels needs to take place over this ramping period with various candidate technologies out in future towards 2040 and 2050. So battery electric is obviously one of the candidates, but there are a couple of candidates linked to hydrogen powered, so fuel cell technology, but also engines based on running hydrogen. And of course, other types of combustion technologies with drop-in fuels, e-fuels, biofuels, etc. So this technology mix, it's clear that there's no single silver bullet, as it were. There's no single technology which is a clear winner at this point in time. And a lot of the market, the companies need to explore these different technologies. And that's very important from a policy perspective also, that they allow fair competition between those technologies. So this is another view of the same type of strategy. Now thinking about it, if we are really going to switch towards zero-emission technologies, we want to have renewable technologies as a baseline. Those are typically producing electricity. So from the grid, of course, we can feed those to battery electric vehicles. Conversely, we could convert that into hydrogen. As mentioned, that can be used within a fuel cell electric vehicle, or in combustion engine vehicle. But there are other pathways out there to maybe support bio or e-fuels to be used in hybrids, whether they're plug-in hybrids or non-plug-in hybrids, or to have other types of combustion. Today, I'm mainly going to be focusing on the fully electric and the hydrogen route, since very often the e-fuel technology is keeping, especially in terms of the combustion engine, is keeping existing technology, but addressing the CO2 reduction upstream. So for hydrogen, the question is, where will the hydrogen come from? This is an image from a presentation made last year by Fraunhofer, which gives some of the idea where hydrogen could be produced globally. So within Europe, yes, there is potential to produce hydrogen, but it's dwarfed by the production potential in the Middle East and Africa in terms of nearby areas. Of course, Middle East is producing a lot of the fuels that we use today, but maybe some of the lower cost green hydrogen can come from these areas in future. The question is then how we get that hydrogen or the electricity produced by renewables in that area towards Europe. Of course, there are options to run electricity lines from those regions all the way to Europe, or even to have hydrogen pipelines. Of course, there are infrastructure challenges in doing that. It's also challenging from a security viewpoint. But at least it's a route for the energy to get into Europe if we choose to be reliant on those areas. Another way of dealing with it then is to use a lot of the existing infrastructure which comes from the Middle East. And the choices there are to switch to other types of energy carriers. So starting from hydrogen, it's possible to liquefy hydrogen or highly compress it and to ship it rather than use pipelines across, or to convert to some other energy carriers such as ammonia and methanol, which again, I'm not going to discuss today. But the projections here, so this is a study looking at the Saudi Arabia region with some kind of cost projections of what might be possible for hydrogen production by 2030. So perhaps as low as 4.6 euros per kilogram. Again, transport costs for liquid hydrogen and pipeline costs need to be taken into account when we're thinking about the transport of the energy from those regions. If we look from the demand side, so rather than looking only at the supply, how vehicles are used, this is a study completed between TNO and Transport Environment about how both rigid and long-haul vehicles are used in practice. So on the y-axis, you have the fleet share of daily driven emissions and the typical daily distances driven from those vehicles. And you can see for the rigids, they center around 300 kilometers per day. And the articulated, so the heavy-duty trucks that can do up to including long-haul, there are very few of them that actually do 800 plus kilometers per day. So the majority is in this region. And the argument made, or the study here, is to look at what degree of this can be supported by hydrogen, what can be supported by fully electric. But it's worth noting that the types of solutions here, and we'll come back and talk about this later on, are very dependent on the types of logistic patterns for the suitability of each of the technologies. Certainly then, as these vehicles come into rest, the availability of the infrastructure is really key. So if we pick an easy example here to think about, this is a Dutch supermarket which operates in terms of distributing goods up to and around Amsterdam. and returns to other distribution locations. The way that this vehicle drives, it starts early in the morning. In a stylized way, it drives for 3 hours. It spends an hour in the distribution center where the driver is perhaps taking a break. The goods are being loaded and unloaded here. And then it repeats this with other distribution centers over the course of the day. So this is typically 4 to 5 trips per day, maybe up to 450 kilometers per day. But these breaks are returning to locations which are owned by the supermarket very often, or at least can have charging infrastructure or refueling infrastructure in place. So these types of logistic patterns are more easy to consider electrification or own solutions between the vehicle and infrastructure versus being spread out over a larger geographical distance. What's also looked at with these types of operation are, of course, this is a very stylized way of looking at things. In reality, there's a lot of variability in the type of driving per trip, the variability on the distance per trip, and also some of the start times. So these 1 hour periods are not exactly 1 hour. So understanding the logistics is quite key to coming up with what technical solutions can be suitable for each of these logistic use cases. So this is a bit of a look into more detail at actually running these vehicles in practice. What I want to illustrate with this is a year in 2019. These were with very early electric trucks, looking at the different days of the week, and how that matured over the course of a year to 2020. And what you notice down here, so the light blue here is the planned kilometers, and the various colors are the actual kilometers driven per that day in that week. What you saw in general is that the planners were very conservative in the way that they were using these vehicles. They were very unsure about the range. They were still learning how to use those vehicles, but also the actual driven kilometers were sometimes very different than what was planned. So it took a full year in that learning process to increase the number of kilometers driven much closer to the vehicle capabilities. But also the planners got very good in understanding the difference between what was planned and what could be realized in practice. And one of the ways that they were able to do that is to incorporate models, so physical or digital twins of the actual physical trucks, to understand the influence of payload, driving conditions, route, vehicle age, etc. And to illustrate what we mean by this, so a digital twin is a model, but it's a model whose parameters and states are updated from the actual vehicle. And the way these types of software representations are used are to feed back into things like charge planning, into energy management. And this is a circular approach to using models in the planning process. A lot of these then run in the cloud and are coupled in a concurrent way to the actual physical truck. So also bottom right, you can see where this is important. So this is the actual available range over the course of the year. And you can see a trend here from 4 trucks which were being used. What you notice in the summer periods, the actual achievable range is much higher than in the winter. This is quite common for electric vehicles. But taking this into account in the planning, in combination with the driver, the effect of the payload, the vehicle age, etc., means that these vehicles can be more effectively used. But the message behind this slide is it took a full year to get more competent with new tools, new ways of logistic planning, also better understanding for the driver. So this technology adoption rate is very important to take the end user and the logistic situations into account. So it's not also only about range. Range, of course, affects delivery and distribution vehicles. But a lot of the vehicles which are covered under the CO2 reduction are things like construction vehicles and refuse rubbish trucks in operation. And some of these have a very high energy consumption from auxiliary systems, which in some instances can be 50% of the energy that they're using. So again, understanding the auxiliary use from the vehicle, whether that's heating and cooling systems, whether that's auxiliary use, is really important to include in your logistical planning and understanding actually what kind of utility you can get out of these vehicles in practice. One of the main challenges with introducing any new technology which is different from conventional vehicles is in terms of cost. So this problem is quite well known. If you look at the total cost of ownership, so that's both the initial capital expenditure and the operational cost of the vehicle over its lifetime, for a lot of the regional distribution cases, maybe the cost of the diesel is a third of the total cost. The initial cost of the vehicle is 10, 11%. Operating the vehicle, of course, requires a driver to be present, and then you have other types of costs involved in maintenance, etc. What happens when you go to electric vehicles is the energy cost can be lower, but clearly the initial upfront cost of the vehicle is significantly higher. So as we move to these new technologies, the capex is increasing. There's a lot of upfront cost and commitment, although in the long run, depending on how much you use the vehicle, the operational cost decreases. So to view that in terms of timeline, you have the upfront cost, the value of the asset. You may have a multi-owner model. You may have a single owner over the lifetime of the vehicle. But typically, the payback period desired by the first owner is of the order of 4 to 5 years, sometimes shorter in terms of a leasing company. Whereas the design life of the vehicle, classically for heavy duty, it's considered 8 years or 1 million kilometers. Typically, the European lifespan for a truck is 11 to 12 years. So over that period, there needs to be enough operational cost saving to counterbalance the initial capex investment. One comment on this figure. So firstly, it's not necessarily linear. It can be a very different form of curve depending on the depreciation of the vehicle. What we also don't yet know is at end of life, a lot of the battery vehicles will have a battery still present that normally needs to be recycled. Normally that's at cost. The second life battery market is not very established. It may be that there's some residual value that can be recovered here, which helps with this capex challenge. The other aspect to mention here is that the design life for the vehicles may be very different for different types of technologies. It could be the case that electric might last even longer than the 8 years that we see with conventional vehicles. So I had a look for some studies to compare some of the candidate technologies here. So this is a study produced just over a year ago by ICCT, which is a research organization looking at these types of questions as well. From the new technologies, what you see are very often the candidates of fully electric, fuel cell electric, and hydrogen combustion technologies being considered as suitable candidates for the market to reach a zero emission. I should caveat this graph with saying that this is a US example, long haul, but it's one of the few examples where these types of technologies are compared with various assumptions in place. And we'll talk about those assumptions in a bit. But what you can see here is you have the diesel ICE baseline. You have TCO for the fully electric reducing over the years here, and eventually being competitive with the diesel equivalent. For the two hydrogen candidates, this is very sensitive to the cost of green hydrogen, but you see cost reduction some cost reduction for the hydrogen engine-based vehicle, and quite a bit of cost reduction potential for the fuel cell vehicle. So this is, of course, dependent on things like market take-up, technology maturity. But whenever you see these types of studies, it's very important to understand the sensitivities and the types of assumptions that they made. So I have on the right-hand side here the sort of assumptions which are made here. And this study did do the right thing and went into some of the sensitivity analysis. And I'll spend a few slides on this. So depending on the green hydrogen costs versus either public or private charging costs, you often get these types of bifurcation analysis. So here, this is the cost of hydrogen on the y-axis. This is the cost of charging the electric part on this axis. So anything above this break-even line, battery electric trucks will be cheaper. Anything below will mean that fuel cell electric or hydrogen trucks can be cheaper. In this case, it's the fuel cell electric, which is the main hydrogen candidate. Again, this is very depending on the sensitivity. So in this figure, they did indicate for the US market where they expect by 2030 the hydrogen price range to be, where they expect the charging cost to be. And seeing how far away it is from the sensitivity gives you some idea of, let's say, the competitiveness of other technologies. Again, to avoid dogmatism, I should caveat this, which is it's very dependent on charging infrastructure and refueling infrastructure to actually what technology makes the most sense. But it's to spend a bit more time, it's very important to understand sensitivities here of which technology makes sense for which country, which logistic situation. So this also is a figure from Scania. So it's also exploring sensitivities. What you have now here are looking at the types of cargo here. So at the bottom, weight constrained transportation versus volume constrained transportation. And here with the trip distances along here. So each color represents the type of cost sensitivity here. And on this side, the energy price sensitivity. So this is system cost. This is using lithium iron phosphate battery technology. So everywhere in this region, the full electric using this battery technology is the best in terms of most cost-effective technology. For the weight constrained, it's worth going to more energy-dense batteries. And then you have the line here, which is splitting out the fully electric on this side and the hydrogen on this side. So again, this is with all things being equal, with some assumptions about the cost per kilowatt hour of the various technologies. And for the energy sensitivity, the same type of figure, but then looking at the cost per kilogram for hydrogen, cost per kilowatt hour for electricity. So again, to take a sample of how other people have done this, this is from Daimler. Similar type of sensitivity analysis, looking at the cost per kilowatt hour for electric and the cost for hydrogen on the x-axis. So here, if the cost of the electricity is high and the cost of hydrogen is low, if you end up here, hydrogen will be more favorable. If you're below the line, electric will be more favorable. What Daimler did in this study as well is they looked at specific countries. So each flag represents for each axis where the cost of the electricity of the charging and the cost of the hydrogen is. So we see quite some differences in the cost of hydrogen across different member states. And the conclusion here, this is firstly looking at depot charging. It's very difficult to compete with fully electric for depot charging, like the supermarket case that I presented earlier. If you look at public charging, longer distances where perhaps electricity might be more expensive, this is how it looks at the moment. So there's really a big spread of hydrogen. Again, given some of the arguments I presented at the beginning for the potential of cost reduction of the hydrogen, if they move in this direction, you do get some advantages for hydrogen refueling versus more expensive public charging. So from an electric perspective, it's very important to keep public charging costs down. Of course, it's important from the hydrogen side to get these large-scale cost of green hydrogen down. But this sensitivity is perhaps where it will play out.
Stephen, before you go to the next chapter, there's one question from Antonina.
Yes.
Regarding the TCO calculations that you just shared. How applicable is this US example to Europe? The regulations may be quite different, influencing TCO calculations.
Yeah, so as it's a good question. So the other study that I presented earlier is central to a European one. Yes, that comment is correct. What I was looking here, as I described, was really looking at these three candidate technologies to compare. It is a US example. I've not yet found a European example where we look at these three technologies back to back. Maybe that's in progress at the moment. I hope that answers the question.
Thank you.
Okay. So challenge two then are the vehicles. So how can we provide affordable and, of course, efficient vehicles? So here I'm going to spend a bit more time talking about the fully electric solution. So what we see, we are really producing the first generations of electric vehicles. So a lot of the OEMs, when they looked at producing electric trucks the first time around, most of it was conversion of existing combustion engine platforms towards an electric powertrain. That involved taking out the engine, but leaving most of the design of the chassis in place, most of the transmission in place, and like for like swapping out, often with a single electric motor in place of the engine. With the second generation, there was a bit more optimization, maybe focus on charging capabilities, perhaps integration of new components such as e-axle, but a bit more optimized. There have been a lot of European projects looking at these types of vehicles as well. So the size, the topology, so which types of motors and gears can be used, the right sizing of the battery pack and technology selection. But where we want to head is towards third generation. So this kind of native electric trucks, where rather than refitting a new powertrain technology to an existing way of working, there's the opportunity to clean sheet design the truck from scratch, to think about optimization of the battery pack, maybe innovations in terms of the transmission technology, right sizing of the components. And the same type of thing is happening, of course, with the fuel cell. There's optimal balancing of the fuel cell and the battery. So remembering that fuel cell electric are also electric vehicles. And there are a lot of European projects looking at these types of topics. The one that we're linked to today is NextETRUCK, which is looking at the next generation of medium-duty electric trucks. So how might these vehicles change? So if we look at it from above, this is the typical design for a combustion-based vehicle and early first-generation electric vehicles. Things are distributed. The batteries are put in place of the diesel fuel tank, but of course there's a lot more space to think about optimal placement here of designing around the battery, perhaps rethinking how the transmission and motors are working. I don't think we'll ever get as far as this image at the bottom. This is thanks to Auker at Zenmo and TUE. But at least this type of approach of how we rethink the design of the vehicles from the technology viewpoint. So again, like mentioned here, there are options to rethink the transmission with electric motors and gearing. There are a lot more options. Very often the motors are a lot smaller in terms of torque. You can also combine different types of motors and gears together to focus on power, performance, acceleration, or efficiency. So on the left here, you had the first iteration of the Tesla Semi. Then you have eventually what Tesla included, which was 3 geared motors on their transmission system. This is a 6x4 configuration. So maybe there are other types of options. But from the market as well, you see other types of solutions coming in. So this was an early development e-axle. There are more and more commercially available electric axles coming in, which are, again, a different way of thinking about the design of these vehicles. Actually, Volvo presented this at IAA last year. So the Volvo e-axle, which they use in their FH platform, has 2 electric motors geared in there. And that gives, of course, a lot more possibility for efficiency gains and optimization. There's some of the statistics here. But this is one area on the transmission, the optimization of the electric motors and how they're used within the trucks, which is ongoing. Then the other obvious area are the batteries which are used within the vehicles. So I brought up this figure. This was produced within the working groups within Battery Europe, and it set numbers from 2020 and where we should target these capabilities for these battery systems to be by 2030. So typical size for 2020 was in the range of 150 to 600 kilowatt hours. Perhaps by 2030, we'll get up to 1,000 kilowatt hours, so 1 megawatt hour battery pack. But several things have to happen to highlight those here. Firstly, the energy density at cell level needs to improve. So when this was defined back in 2020, they were targeting 250 watt hours per kilogram. The target for 2030 is to get that up to 450. Also, the cycle life would need to improve. And the main one for the TCO impact is the cost reduction. So coming down from 400 euros per kilowatt hour to 150 at pack level. We've already had some indications in the market that things are going in the right direction. Actually, from December 2020, although we've not fully seen it in the market yet, CATL, so a large Chinese manufacturer, were already indicating they could reach 500 watt hours per kilogram. Typically for heavy duty vehicles, the majority of them are using lithium iron phosphate technology. Some of them are using nickel manganese cobalt technology. And there is a push also to have a combination to include manganese into LFP to have better performance for those batteries. But the majority of what we're seeing in the market at the moment is still LFP technology. So this also announced last year, the update on the Volvo FH platform. So for Europe, for the heavy duty segment, Volvo has the majority of the market share at the moment in terms of sales. What they presented was a truck now that could go up to 600 kilometer range, doubling what they originally had as 300. Of course, that was partly due to the redesign, more space for the batteries, but of course also the benefits in terms of efficiency from the electric axle. It's also worth paying attention to what CATL announced last year, so specific for the truck side, a 600 kilowatt hour pack, which could achieve 500 kilometer range with some impressive fast charging capabilities. So they were claiming 4C to charge to 70% in 15 minutes. Also then, if you remember the discussion of what I presented on lifespan, so hitting the 8 years or 1.2 million kilometers, so really designing for the truck life cycle. So again, we wait to see these battery packs come in to market. This is the TechTrans T that was announced last year. So also a bit of a roundup looking at the different vehicles. So this was collected from the IAA 2024. And what I've done here is grouped the main new vehicles that were presented per OEM. And I've given some indication whether they're fully electric, fuel cell, H2ICE or other ICE-based vehicles. There are some details here. If you're interested in having some more information on this, I can share this. What you see, though, is that a lot of the OEMs are keeping their options open in terms of what technologies. So again, this links back to the original point that I made on the big picture. It's not clear which technology is the right fit for which logistics situation. And the OEMs clearly have that view that they're producing the technologies which the market will pick up in some form. Looking a bit about against the EU market, so we do have some steep targets in terms of sales. So what this picture represents on the left, these are the medium duty sales from 2024, the first half of 2024, and these are the heavy duty sales. So the majority of medium duty and heavy duty are diesel based. There are some natural gas and a handful of battery electric. So in the heavy duty segment, 1.2%, 10% for the medium and light duty segment. Top right here, then you see the vehicles. These are some of the main selected vehicles. A lot of the European OEMs, the payload, the range, the battery capacity, what they're claiming in charging time and the gross vehicle weight. So there's a lot more selection coming into the market now. Certainly there's a push up in the range compared to the earlier generations. But we're still at the beginning of an adoption curve here. These are some of the sales for light and medium duties. So 2023 and up to 2024 were better. Same with the heavy duty trucks. But we're still not accelerating rapidly enough. In contrast, to compare that to the Chinese market, so here's similar types of figures from last year from China, where maybe more aggressive policies are in place. They're already at 9% for both medium duty and heavy duty in battery electric. I should say for fuel cell or hydrogen based, it's still around 1% in the other category. The other thing that you see is for the fully electric, this is for medium duty LFP based technologies. The range and the battery capacity is of course improving. Similar story for the heavy duty, where you get some sales volume as well from this. So the technology is improving. We still have to wait and see the effect of some of the policies, subsidies, and legislation coming into effect. Okay, so the third challenge I'd like to talk about is infrastructure. So it's clear that the OEMs are producing technologies in terms of the vehicles. The policy is largely in place to help things along. But we do need infrastructure, whether it's for the electric side or the hydrogen side. So if we think about the numbers for the 2030 vehicle, if we're heading towards 1 megawatt hour, and remember today, the largest battery we have on the market is just over 700 kilowatt hours, so we're already some way towards that. We would want to target 300 to 1,000 kilometer trips with this kind of energy footprint. That does mean that we need quite a large charging power. So we're now needing charging power for the same C rate, for the same charge rate for the battery above 1 megawatt hour. 1 megawatt of charging rather. So that's the equivalent to one of these vehicles coming up of, let's say, 10 Model S Teslas all charging at a very fast rate together. So it's quite a big impact on the grid. Along the main TEN-T corridors, so the main transportation routes, we really need deployed infrastructure to deal with these vehicles in a sensible way. So what is normally the way of thinking about fast charging for long-haul electric trucks are that the driver will drive a maximum of 4.5 hours. Based on legislation, they need to take breaks. The way that you organize those breaks over the day can vary, but during that time, if you're stopping in a lay-by or a point where you can recharge the vehicle, you need charging infrastructure to cover the next leg of the journey. Maybe a simpler way to think about it is how many kilometers of range you can put back into the vehicle per minute of charging time. So existing charging technologies or CCS2 perhaps can cover a large amount of the charging, but for the newer vehicles, we need to go in the 700 to megawatt range to be able to deal, especially if you remember the 4C type technology that was presented earlier. There are technical challenges in terms of efficiency, the thermal management of the charging process, and of the power electronics and charger. But this is being worked on quite heavily. So this is a table produced by Argonne, Ted Bond over in the US. The one that I want to draw your attention to is the MCS, the megawatt level charging standard. So there was a lot of coordination versus what happened on the lower powers of various types of connectors, with the trucks to standardize towards one large connector, which had enough voltage range and current range to deal not only with the trucks in 2030, but beyond. So the peak power can handle 4.5 megawatt. The reason that that's also interesting is that can open up to other types of markets, such as off-road, aviation, and maritime, using the same charging standard. Again, it's liquid cooled. It's a fairly heavy connector, but we're already seeing companies demonstrating this type of megawatt level connector. So I pick one example here. Again, you can see the quite large cable here, 2-meter cable, with liquid cooling inside and the power electronics to support that. So MCS has been worked on. This is coordinated within the US, but also with involvement of standardization committees from Europe. This gives a rough timeline for the standardization or main standards which cover MCS. It's also looked after by the Charon Task Force. So we expect that to be published finally, all of the standards in place by, let's say, late 2025, early 2026. Again, as mentioned, it covers not only the truck, but also aviation, maritime, and mining equipment. So there are many challenges covering charging. This is an image from Scania. There are requirements on public charging infrastructure. So a lot of the logistic companies out there cannot afford their own charging infrastructure. Often it's a small company operating vehicles. They need to make use of public charging infrastructure. Also, if vehicles are covering much larger distances across Europe, they need to make use of charging infrastructure. They can't invest for their own infrastructure throughout. There are lots of initiatives to realize that. Probably the best case commercially is Milence, which is the joint venture. I think this week they're installing some charging points in Italy. But again, it's a challenge of upscaling fast enough. Also, charging is not only the public side. We also need to consider it from depot charging, vehicles that operate in an urban area, a regional area, the long haul area. So public charging is one, but also destination charging. If you take perhaps Port of Rotterdam or some of the main destinations, we need to think in a very efficient way how to deal with that charging problem. Equally, and this comes back to the digital twinning, you need to be able to track the charge over time, make accurate projections of when you need to charge, how much you need to charge. So we need better fleet management and service solutions here. Okay, so this is a picture for what might be a private charging station. You have the main operation of the chargers and the vehicles. You might have local energy storage in the form of a battery. You may even have solar panels on the roof or connection to other types of energy demand. But these types of charging sites, these charging hubs, also need other information to be able to optimize their operation correctly. So making forecasts on the renewables, on the fleet schedules, on other grid pricing, etc. So this is a more complex problem than we're used to with diesel-based vehicles. As mentioned, BESS, energy storage as a solution. So very often you may have a low grid connection, a limited grid connection. If you have a vehicle coming in and intermittently charging, you may need instantaneous power. A BESS solution might be a nice way around that without having a lot of grid reinforcement. And there are various solutions out there. So this is an animation. This is thinking about how trucks can operate. This is Port of Rotterdam. This is one of the main corridors that's running through the Netherlands. This corridor ends up heading into Germany and ultimately to either to Poland or Austria. But where do you place the charging points? How do you combine, let's say, depot-based charging with public charging? How do you deal with peak demand here? Again, this is produced by Zenmo, which is a company looking at this type of problem. So the future public charging sites might look like this. This is an image produced by Heliox, one of the companies producing megawatt level chargers. You may have priority lanes at megawatt, where vehicles come in that really need to charge at a fast rate, but perhaps that's not suitable for every vehicle. You may have ones at a lower power rate that can be organized differently. And you may have, let's say, again, still lower power, but this whole charging site needs to take into account both the high priority fast charging using megawatt level power versus, let's say, the slower charging. That requires inherently a booking system. You need to book your charge slot and your power, determining what duration. And there's a need for automation between the digital twins of the charger of the vehicles and the connection of the charging site to realize that solution as well. So to end on policy, there's quite a need for this infrastructure. This is also part of the CO2 package, and specifically in the alternative fuel infrastructure regulation agreement. This sets some targets for 2030 and beyond. So this, what I show on the screen now is from the white paper from ASEA, the group of OEMs, looking at whether you prioritize CCS at the lower power or the megawatt level charging scenario, or mainly focus on providing the megawatt level charging solutions. And again, this is looking at the fleet hub, public fast highway charging and public overnight, and then considering it from the different use cases of the trucks, whether it's urban, regional, long haul. You can see long haul is mainly connected to the fast public charging. Okay, so there is regulation in place which comes in for 2030. There are some also interim targets for 2025, but this is a challenge for a lot of the member states to realize this in practice. Okay, so lastly, I'd like to end with saying a lot of the topics which I presented today are really the focal point for the NextETRUCK project. So things like the digital twinning, the new design of the vehicles taking into account TCO, the fast charging concepts. And one very important thing mentioned at the beginning of the presentation is to really demonstrate these technologies in real world situations. So there are 6 months of demonstration of 3 candidate vehicles with end users to better understand how these vehicles are used in practice. Okay, with that, I'd like to finish. Yeah, thank you for listening. Maybe there are some questions if we have time.
Yes, we have time. There's a question which is coming from Diego Ruiz. What would be the advantages of H2 ICE vehicles? Wouldn't it be very inefficient compared to hydrogen fuel cell engines? He stated this a couple of minutes ago, so he's referring to the slides a couple of minutes ago.
Cool. It's a good question. I think that the argument for H2 ICE is you're making use of a lot of expertise, factories, facilities around combustion engines, but you're still moving it towards a zero CO2 fuel. So that's the big motivation. It's maybe an easier step for a lot of the OEMs to move towards before, let's say, switching to fuel cell or other types of technology. So that's the argument for it. The arguments against it, yes, you have the same types of costs and challenges for infrastructure, for storage of hydrogen on board. You do have some efficiency limitations. So, for example, since it's non-electric, you don't get the regen braking capability. So these are arguments for and against. Again, there will be markets out there where it makes a lot of sense to use H2 ICE as a solution. I am very careful not to impose an opinion. We happen to be working on an electric truck project. But yeah, there is a lot going on with H2ICE as well.
No, great, thank you. Before I also have a question in case there's nothing coming from the audience. What I would like to highlight is also that we are, as I've stated in the chat, that we are also cooperating with the other projects in the as part of the Albedo cluster, and there we have exchanges. And I also see people here as attendees who participated in workshops uh, from our Albedo cluster cooperation, and we're also talking to cities and regions and how they could support the infrastructure, or what kind of investments need to be made from these public entities. So, for example, Polis had a longer meeting with the German region of Baden-Württemberg, which has also done extensive studies and is currently planning on an expert cooperation and roundtables to plan their charging investment infrastructure, because these areas in the heart of Europe have significant road freight transport challenges ahead, because whenever you cross Europe, that goes through these areas. And now I also have a question to you, Stephen, because since you're observing this for a long time, do you think that the technology shift in the last 5 years regarding hydrogen and battery electric vehicles makes certain things already obsolete? Is the technology changing that quickly, or how do we keep up to date with this?
I think there's a challenge for Europe in general. So I included China here as an example of something that's where you see the effect of policy and state support for some of the solutions, which are ahead of us, at least in terms of sales. I think the main challenge here is not only technical. I think there will be technical solutions, but getting let's say the human capital, getting the training from the end users, seeing the routes for adoption, making sure those tools are available. As I indicated, we had with the supermarket we worked with, that was a learning curve. It takes time, and it's especially challenging for the smaller companies out there to have this adoption, where it's a big investment for a small company to get these types of vehicles in place. So I think we need both technical, but we certainly need non-technical solutions as well. We need a lot of training, sharing experiences, working together. In terms of the question about technology obsolescence, many years ago we were working on hybrid technologies. We saw that, especially for the zero-emission zones, as being a good candidate. You had the benefit of being able to run on an engine outside of the city, switching to fully electric inside the city. Some of the city policies were very challenging, though, to demonstrate that the engine was not running. And in the end, there seems to be less attention now to hybrids than there were. There seems to be a stronger focus, let's say, to the electric and fuel cell for the longer distances. So it's a technology which was in focus and is maybe less in focus now. The other one, which is on the Chinese side, so they have quite some policy on this, is battery swapping. So we see a lot of, even in the heavy duty sector, a lot of initiatives looking at this as an alternative for the charging infrastructure. I don't know if that's the way to go, but maybe there's other innovation in that direction.
Okay, thank you very much, Stephen. Then I will conclude this webinar by saying that this webinar was mostly an introduction to the topic and the results of NextETRUCK, of our project where we are working together, will basically come once we have kicked off the pilots, and they're starting this year. So don't forget to follow us and keep up to date with us through Twitter, but mostly on LinkedIn and our homepage, as I've mentioned before, because once these trucks are driving, and these tests which are taking place in Barcelona, Istanbul, and London with refuse collection trucks and other medium-sized trucks in Istanbul, then we can provide you with more detailed picture from our results, basically. So I'd like to conclude with the words from Simon Edwards in the chat. Dear Stephen, thank you. A model presentation, comprehensive, clear, and yet concise. Thank you very much for the webinar and your work, Stephen.
Thank you.
Okay.
Nice afternoon.
Thank you very much. Then have a good day, and bye-bye.